Thank you for the invitation. So I want to start with a simple argument which I think illustrates the difference between birational transformations and regular automorphisms when you want to study the structure of groups of birational transformations. So let's start with the following example. So you take gamma 1, gamma 2, gamma k, which are regular automorphisms of the affine space, let's say over the field of complex numbers. So you just have a finite number of polynomial transformations of the affine space with polynomial inverses. And assume that each gamma I and its inverse gamma I minus 1, so the inverse transformation, so all of them are defined by formulas, so polynomial formulas with integer coefficients. Okay, so for instance, gamma 1 of, let's say in 2 coordinates, gamma 1 of xy is y minus x squared x. This kind of transformations, okay? And then you look at the group gamma, which is a group generated by this finite number of elements. Okay, so that's a group generated by all of them. So typically it's an infinite group. And the statement is that gamma is residually finite. So what does this mean? This means that you have enough morphisms from gamma to finite groups to distinguish all elements in the group gamma. So for every element alpha in the group, there exists a finite group F, and there exists a morphism phi, such that phi of alpha is not the neutral element. Okay, so in other words, you can embed gamma in its profinite completion. Okay, so I want to prove this. It's quite simple. So you start with an element in gamma. No, I will come back to this later. No. So you start with an element alpha. So it's given by formulas with integer coefficients. Because it's generated by the gamma I. And then you can fix a point with these integer coordinates such that, so of course I said something wrong here. I need to assume that alpha is not the neutral element in gamma. Okay? So alpha is not the identity. So since it's not the identity, I can find a point with integer coefficients, with integer coordinates, so that the image of this point is not the same point. So okay, it's just because if you have a polynomial function which is 0 over the integers, then it's 0. Okay, now you choose a P which is a prime and which is very large compared to all the coefficients all you see in this formula. Okay, then of course alpha of A1 AN is not A1 AN modulo P. Okay. And now you look at the reduction modulo P, and you get a morphism from gamma to the group of automorphisms of the affine space, but not with complex or integer coefficients, with coefficients now in Z mod P's. So you get a morphism into the group of automorphisms of the affine space of dimension n with coefficients in Z mod P. Okay. And the image of alpha is not the identity in this group because of this relation. But this is not the end of the argument because this group is not a finite group. So it's an infinite group, at least if the dimension n is not 1. It contains all transformations of type. Let's say in dimension 2, it contains all transformations of type x, y goes to x plus y to the d, y. Okay. So you need to replace this group now by a finite group. And what you do is, since you have regular automorphisms with coefficients in Z mod P, each element in this group acts just by permutations on the set of points. And so you map this group into, to the group of permutations of the set of points in the affine space. So now you compose with the morphism to the set of permutations of the finite set. So Fp is just C mod Pz. So this is a finite set, P to the n elements. So it's a finite group. And by construction, the image of alpha is a non-trivial permutation. So you win. Okay. Okay. So now, of course, you can improve this statement because if you start with finitely many polynomial automorphisms of the affine space, then you write the formulas for these automorphisms and for the inverses, and you see only finitely many coefficients. Okay. So in fact, as soon as you start with finitely many regular automorphisms, the coefficients which are involved for the group gamma are contained in a ring which is finitely generated. Okay? And so replacing this argument of reduction mod P by reduction modulo some maximal ideal, in fact, this argument applies for all finitely generated subgroup in this group. Okay, so this assumption is not needed, in fact. Okay, and you get the same conclusion. And of course, what I said for the group of regular automorphisms of the affine space of dimension n, you can put here any algebraic variety. Okay, you can replace the affine space by an algebraic variety. Okay, complex algebraic variety. And you get the same statement for regular automorphisms of algebraic variety. So this is due to Bass and Lubotsky. The same result for groups of linear transformations of a complex vector space is due to Malchev. Okay, so it was known before for linear transformation, and Bass and Lubotsky adapted the argument for regular automorphisms. Okay, so now let's try to do the same thing for birational transformations. So you start with, let's say, birational transformations of the affine space defined by formulas with integer coefficients. Then you can do exactly the same argument, but the problem is at the very end of the argument, because here the group of birational transformations of the affine space does not act on the set of points because of indeterminacy points. Okay? So, for instance, you start with the group gamma, which is the group SL3Z, that you view as a, let's say, PSL3Z, as a subgroup of PGL3 acting on P2. And so let's say this is the first group. And the second group is gamma is this group, PSL3Z. And you add one extra element, and you look at the group which is generated by PSL3 and sigma. Sigma is just the standard quadratic involution. So it's 1 over x, 1 over y, 1 over z. Okay, so it has indeterminacy points like this one. Okay, so when you look at the group generated by these two transform, I mean this one and this one, so this group is finitely generated. There are indeterminacy points for elements in this group. But now, since this point is an indeterminacy point for sigma, when you apply PSL3Z and you conjugate sigma by element in PSL3Z, you can move this point to other indeterminacy points. And if you do the reduction modulo P, PSL3Z surjects onto PSL3 FP, and this point is mapped to every point of the set of points with coordinate in FP on P2. Okay, so PSL3Z mod P of 1, 0, 0 is P2 of FP. So all points are, in fact, indeterminacy points for this group. Okay, so this argument breaks down if you replace automorphisms by birational transformations. And actually, I think it's not known. So the question is, are finitely generated subgroups of birational transformations of Pn, let's say over the field of complex numbers, so are such groups are residually finite? I don't know the answer, and I think nobody knows the answer. Okay, so this was just an example to stress a difference between regular automorphisms, even of affine spaces, so even for this type of infinite dimensional group, and birational transformations with indeterminacy points. Excuse me? In this example, actually, it's a good question. I think I can do it, yeah, but I think nobody did it. Yeah. And PSL3Z is residually finite. Yeah, yes, it is. Okay. So what I want to explain today is a strategy which does not apply to all groups, but a certain type of groups. And you start with such a type of group acting by birational transformation. And you do a modification, and at the end, you get a group which is not a group of birational transformations, but a group of pseudo-automorphisms. So you remove all the problem coming from hypersurfaces which are contracted. You don't remove all problems coming from indeterminacy points, but at least you kill all hypersurfaces which are contracted by elements in the group. So here is a statement. Say theorem A. So I forgot to say it, but it's a joint work with Yves de Cornulier. So you start with X, which is a smooth, complex projective variety. And a group gamma, which is contained in the group of birational transformations of X. And now you assume that gamma is a rich group in the following sense. Gamma has the so-called property FW. So I will come back to this property. And the conclusion is Then there exists a y, a smooth projective variety. There exists phi from y to x, a birational morphism. And there exists u in y, a Zariski open subset. With the following property. So first, u is just the complement of finitely many hypersurfaces. So each EI is an irreducible hypersurface. And second, when you conjugate gamma acting on x by phi, so you get a subgroup which is gamma conjugated by phi. So it's a subgroup of the group of birational transformations of y. Then this group, in fact, is contained in the group of pseudo automorphisms of the open set U. So on some large open subset, the group acts by pseudo automorphisms. Okay, I will define. So there are two, I think, that need to be described in details. So the first one is property FW. Okay, I will come back to this property in a few minutes. Examples of group with this property are SL3Z or SLMZ with m larger than 3, SL2 of Z square root of D, say a D square free. Examples which are so examples that do not satisfy this FW property are abelian groups or free groups. So it's, okay. Excuse me? Okay. So this is a fixed point property, that's the F. And W is spaces with walls. Okay. So, okay, it's something coming from geometric group theory. So they have a lot of fixed point properties that they study. And so,
are we supposed to think of this as a very special property or kind of a general property?
okay, so it's implied by property T. So property T is not a very special property. It's something you find everywhere. I mean, everywhere in the sense that it's very useful and many groups have property T. So property T implies this property FW. So that's why lattices in higher rank simple Lie groups satisfy property T, property FW. This one does not satisfy property T because it's contained in SL2, but it does satisfy FW. And trust me, I will spend like half of the talk describing this property FW. So just wait for a few minutes. And the second thing is pseudo-automorphisms. Okay, so this, I guess most people in the audience know what pseudo-automorphisms are. So, pseudo-automorphisms. So let's say F from X to X prime birational map is a pseudo-isomorphism if F is isomorphism in codimension 1. Okay, which means that you can find an open subset V in X, so it's Zariski open, W in X prime, Zariski open, such that the codimension of V and W is at least 2. So by this I mean that V is obtained from X by removing a Zariski closed subset of codimension at least 2. Yeah, the complement. Okay. You're right. Yeah, yes, you're right. So X minus V, X prime minus W. Is that correct now? Yeah, it is. Okay. So this means that, yeah.
Is your conclusion that for your gamma y, you have a V and a W nets which work for every element of gamma y?
Oh, it's a group. The group is contained in this, so it's uniform. It does not depend on the elements. Okay, so you do some surgery, so you blow up X, then you remove.
Yeah, that's what I'm asking.
The open subset U does not depend on the element. So there is a statement, and in the statement, the open subset is U. U does not depend on the element. And then here, the notion of pseudo-isomorphism, of course, V and W depend on the element. Okay, so let's do it in dimension 3, okay? So you are in dimension 3. You have a group of birational transformation of, let's say, P3, with this strange property that I need to describe. Then what you can do, you can just blow up P3 finitely many times. Then you remove finitely many surfaces. And in the complement, when you look at the action of gamma after conjugacy, what you see in this complement, U, you may have indeterminacy points, but there is no surface which is blown down. That's a statement. Okay? So all the problems, they come in codimension 2, not in codimension 1. Oh, such that F, when you restrict to V, it's from V to W, is an isomorphism. Okay? So this means that, basically this means that the Jacobian determinant of F does not vanish in the complement of the indeterminacy points. Okay? But you need to be careful because X and X prime are not assumed here to be projective varieties. Okay? So for instance, you take a linear projective transformation of P2 and you remove a line which is not fixed. Then on the complement, which is an affine plane, the transformation is not a pseudo-automorphism because it maps a line to infinity. Okay, so it maps something of codimension 1 to infinity. Okay. Let's do a few. So the pseudo-automorphisms are just pseudo-isomorphism from X to X. They form a group. And let me give a few remarks. Let's do an example. What is a group of pseudo-automorphisms of the affine space? It's just a group of regular automorphisms of the affine space. Because if you take an element in this group, so it's a birational transformation, so you can write it like that. where Pi and Qi are polynomial functions without common factors. So if Qi has degree, I mean, if Qi is not constant, then it vanishes along a hypersurface. And this hypersurface is mapped to infinity. Okay, so this hypersurface is contained in the indeterminacy point of gamma if you look at gamma as a map from the affine space to itself. Okay? So if it is a pseudo-automorphism, all Qi, they must have degree 0. Okay, so in fact, it's just a polynomial transformation. Okay? So if you have a group, I mean, the group of pseudo-automorphisms is just a group of automorphisms. So this means that in this statement, you have two extreme cases. Okay? If you apply this statement, the first extreme case is when the hypersurfaces that you remove form something which is big, in the sense that there is an ample divisor with support coinciding with this union of hypersurfaces. Then the complement U is just affine. And the same argument applies and tells you that you can improve the conclusion and replace pseudo by automorphisms. Okay? And the second extreme case is when, in fact, you don't need to remove any hypersurface. Okay? Then U is just the projective variety Y. And then the fact that pseudo-automorphisms are isomorphisms in codimension 1 implies that the group of pseudo-automorphisms of Y acts linearly on the Néron-Severi group of Y. So the action on the Néron-Severi group is nice. Okay? It's just a linear representation of your group. So you can use techniques from linear representation theory, and somehow you escape the world of birational transformations. You can apply new tools. Okay, so the two extreme cases are regular automorphisms of affine varieties and groups of pseudo-automorphisms of projective varieties. Okay. So let's do it as second remark. So if U is Y, then gamma is contained in the group of pseudo-automorphisms of Y, and this group, there is a morphism into the group of linear transformations of the Néron-Severi group. And in fact, the kernel of this linear representation up to finite index is just the group, I mean, the connected component in the group of automorphisms of Y up to finite index. Okay, so you can split the study of this group by looking at this linear representation and then looking at the kernel, which up to finite index is just a Lie group, an algebraic Lie group. Okay, so this is the first statement. Now let me state the second statement. Before I do state it, maybe I should make one more comment on the first one. So there are situations for which this theorem is completely useless. Okay? For instance, start with X, which is just a Calabi-Yau variety. Then the group of birational transformations of X is equal to the group of pseudo-automorphisms of X, because the fact that the canonical bundle is trivial tells you that there is no hypersurface which is contracted. And then the statement says nothing. Okay, so for groups of pseudo-automorphisms, the statement is useless. Okay? But again, there are other tools that maybe you can use to study this kind of groups. Okay, so theorem B is for surfaces. So I told you that pseudo-automorphisms of, maybe I didn't say it, but I say it now. Pseudo-automorphisms of projective varieties, for instance, that don't have isolated indeterminacy points. Okay, so that's a simple exercise. So if you apply this in the case of surfaces, of course, pseudo-automorphisms, it's just like regular automorphisms. Okay? And there are issues when the surface is not complete, but and so you can improve this type of statement in the case where the variety X has dimension 2. So you start with a surface. And then you take a group of birational transformations in X with a property FW. And then the conclusion is, so assume that gamma is not a finite group. So the number of elements is infinite. Then the conclusion is the following. So there is a birational map, and there is a gamma prime in gamma, a finite index subgroup. Such that first, Y is P2 or a ruled surface, in fact, a minimal ruled surface. And two, when you conjugate maybe not gamma, but gamma prime, then it's contained in the group of automorphisms of Y, and in fact the group, the connected component of the identity. Okay, so for P2, this means that the group is contained in PGL3. For P1 times P1, this means that the group is contained in PGL2 times PGL2, and so you just have a list of I mean, you end up with a finite dimensional group. That's the important result. Okay? So this type of statement gives you, for instance, a complete classification of all possible birational actions of SL2 of this type of group, of SL2 Z of square root of 5. You start with this group. This group has property W, FW. You apply theorem B and you get a complete classification of all possible actions by birational transformations on surfaces. Yeah.
Does theorem B imply that gamma is very finite?
Yes. Okay.
Sorry, so what happens if X is just the square of an elliptic curve and you act by GL to Z?
GL2Z does not have property FW.
Okay, actually this subgroup SL2Z.
A subgroup of SL2Z does not have property FW.
Yes, I think one is square free, isn't it?
Oh,
SL2Z.
okay. So I made a mistake a few minutes ago. Okay. So. So you see, this group is much larger than SL2Z.
Yeah, but if the elliptic curve has complex multiplication, then you act with SL2 with the integers in exactly.
Like SL2Z of I, okay?
Yeah, exactly integers.
Like this one.
Yes.
Doesn't have property of W. Okay, I explain property of W, okay? Because time is running fast and okay, property of W. Okay, so this has nothing to do with algebraic geometry, so it's just a concept for groups. So you start with a group gamma. Type of group I have in mind are finitely generated groups. So let's put this in. Because maybe I will implicitly assume it. And now you look at an action of gamma on a set. So H is just a set. Okay, and gamma acts on H. Okay. And now you take a subset A in H. Okay. Then you say that gamma commensurates A, or more precisely, the action of gamma on H commensurates A if for every element in your group, when you look at what happens to A when you apply gamma, you compute the symmetric difference. So this is just gamma of A minus A, and you take the union with A minus gamma of A. So you look at the difference between the two sets, then the number of elements in this difference is finite. So let me call it LA of gamma, then this is fine. Okay, so commensurating means this inequality. Okay, so you cannot move A far apart from itself in such a way that the difference is infinite. So example is Z acting on Z by translation. You can take A to be just one point. I mean, if A is finite, this is automatic. Or you can take A to be the set of positive integers. You see, if you take half the integers and you translate, then the symmetric difference is just finite. Okay. But of course, this difference depends on gamma. Okay, it's not uniform on gamma. So that's the definition of commensurating. Now comes the definition of, you say that gamma almost fixes A if there exists a set B in H such that first B is fixed by gamma. And the difference between A and B is finite. Okay? So for instance, if you start with a finite set, you can take B to be just the empty set. So all finite sets are commensurated, but they are all almost fixed. Okay. But if you look at the second example, there is no way in which you can replace A by a set B which is fixed by translations with a finite difference. Okay, now comes the definition. So gamma has a property FW if for every action of gamma on a set H and for every subset A in H, if A is commensurated, then automatically A is almost fixed. Okay. So it's a property of the group, and to verify the property, it seems completely hopeless because you need to consider all actions of gamma on all possible sets, and all subsets A which are commensurated, and you want to see whether they are fixed, almost. Okay? But there are techniques to prove property FW. So the main example is property T, which I won't define because I don't have time, implies FW. So for instance, all lattices in simple higher rank Lie groups have this property. So like SL3Z or other lattices in SL3R. Yes and no, yeah, so no. Okay. Okay, so let me explain how you can use this property FW. Okay, so I want to explain the relationship between this definition here and the FW, which is a fixed point on the walls. I mean, on spaces with walls. So you take a tree, let's say a infinite tree like that. And assume that gamma acts by isomorphisms, I mean isometries on T. So you have an abstract group gamma, okay, and it acts on the tree, so meaning that it maps vertices to vertices, edges to edges, and if two vertices are connected by one edge, then the images are also connected by the image of the edge. Okay. So now assume gamma has property FW, and I want to show that gamma fixes a vertex or maybe an edge. Maybe it fixes an edge and switch the two extremities of the edge. Okay, I want to show that. So that's my starting configuration, and now I need to explain how I apply this property. So H will be the space of oriented edges. So a point in H is just an edge like that. So choose an edge. Okay? So an oriented edge is, you see, it's a way to cut the graph, and you can look at what at all points which are on one side of the edge and all points which are on the other side. Okay? So an oriented edge is like a wall, and the wall is you cut the graph here, and you separate the graph into connected components. Okay? So that's my space of walls. And A is the set of edges pointing to a fixed point, let's say Q. So I fix a vertex Q, and I look at all edges that point towards Q. Okay, so this one is not an edge in A, this one is. Okay. Now you take an element in your group gamma. So it takes the point Q, and you take gamma of Q. Let's say gamma of Q is here. Okay. Now you take the set of edges pointing toward Q is moved to the set of edges pointing toward gamma of Q. And the difference between the two sets is finite. It's just the set of edges in between Q and gamma of Q. So A is commensurated, and in fact you have an explicit description. A is the distance between Q and gamma of Q, the combinatorial distance. Maybe with a factor of 2. Yeah, 2. Okay. So this means that if gamma has property FW, then I can find a set of edges which I denote by B, and B is A up to a finite difference. Okay. But then this implies that the symmetric difference between gamma of A and A is bounded by 2 times the difference between A and B, because B is fixed. Okay. So this means that this function is bounded. It's bounded by something like the distance between A and B. Okay, so the orbit of the point Q under the group gamma is bounded. Okay? So you look at this orbit, you get a finite subset of the tree, and you consider the smallest subtree, finite subtree, which contains all this orbit. Okay? You get a finite tree, and you take the barycenter of this tree, that's a fixed point. Okay, so I think now the end of the proof is clear. Okay, let me give another example. Which is essentially due to Farley. It's the following. So you so it's a subgroup of which group of so the group I will look at is the following one. So it's a group of piecewise PSL to the homeomorphisms of the circle or mod C. Okay. Then I say that if gamma has property FW, then gamma is finite. Okay, so what is Q piecewise PSL to the? So this means that you have homeomorphisms from the circle to the circle. Okay, but homeomorphisms which are piecewise. So you have a decomposition of the circle in finitely many intervals at the source. And the target is also cutted in finitely many intervals. The homeomorphism maps intervals to intervals in the two partitions. And the map from one interval to the other one is just a linear projective transformation with integer coefficients. And moreover, the endpoints of the intervals are rational points. Okay? So if you have such a group, then automatically FW implies finite. Okay? So is finite. And the idea behind this statement is closely related to the idea I described for trees, because you can organize rational numbers using binary trees. So it's a Farley algorithm. You know that if you start with the segment with extremities 0 and 1. So I write 0 as 0 over 1 and 1 over 1 for 1. And then you can just produce all rational numbers like this. So you start with these two rational numbers, and then you add up as my daughter did last week. So you just like that. Okay, and then you continue. So you add up above and below. So I add 0 and 1, I get 1, and 1 and 2, I get 3. And then here I get 2/3. And you continue like that. Okay, you see, you produce all, so here it's 1 over 4, etc. So you produce all rational numbers this way. Each time you do it, you double the number of rational points, and you get all of them. Okay? But then you organize the rational numbers in a d-adic way with a tree, because you have, at the beginning, you just have the two extremities, and then when you cut, you get two segments, and then when you cut again, you get two segments, and so on. And elements in PSL2Z are exactly elements of the, transformation, preserving this d-adic order on the rational numbers. So that's a link between actions on trees and this thing. Okay, so let me now use the last minutes to say how we prove theorem A and how theorem B is related to these two statements for actions on trees and actions on circles. So this will be extremely sketchy, but I think the main idea is simple and is modulo technical details. It's easy to understand. So you start with a group, gamma, which acts by birational transformation of X. And X is a smooth projective. Okay. And I want to apply this property FW. So I will assume that gamma has property FW, and I want to use this property. So to use it, I need a set, and I need a commensurated subset, and know what the conclusion is. So the set is, H is a set of irreducible hypersurfaces in all models, I would say, of X. Okay, so the set I will consider is what? You start with all hypersurfaces in X, but if you have a birational transformation, this birational transformation may contract the hypersurface to a codimension 2 or higher codimension subset. Then this hypersurface is not mapped to an hypersurface of X. But if you resolve the indeterminacies of the inverse, then you see where the hypersurface goes. Okay, so you need to put together all hypersurfaces in all models that you need to resolve all indeterminacies. And of course, you need to identify hypersurfaces in two models if they are the same. And the same, being the same is that the birational map from the first model to the second maps your first hypersurface to the second one when you look at the strict transform.
Then do the same discrete variation on the...
Yes, you can phrase it in terms of discrete variations. But I didn't do that, but I'm sure you can. Okay, now what is the set A? A is the set of irreducible hypersurfaces that you already see in X. Those coming from the starting variety X. And now the group gamma acts on irreducible hypersurfaces. It's what I told you, it's just by strict transform when you resolve indeterminacies. Okay? So that's so gamma acts by permutations on H, and gamma commensurates. So that's the first thing you need to prove, and the second one. The very first thing you need to prove is that you can define such a set H, then that the group gamma acts and that it commensurates A. So let me prove the second one. So this is easy. You take an element in gamma. So gamma is a birational transformation of X. And you take a hypersurface W in X. And you look at gamma of W. Okay? So that's a strict transform. Okay. So there are two cases. Either the strict transform is contained in X, so W is an element of A which is mapped to an element of A, or gamma contracts W, and then the image of W by the action of the group is not in A. It's mapped to a hypersurface which lies in a model of X, but not in X. Okay? But you see that the number of surfaces which, hypersurfaces W, which are in A, but which are not mapped in A, they all come from the surfaces, the hypersurfaces which are blown down by gamma. And there are only finitely many of them. So let me denote this by W is contained in the exceptional locus of gamma. And then you get that gamma A, a symmetric difference with A, is bounded by the number of elements, the number of irreducible components in the exceptional set of gamma plus the number of irreducible components in the exceptional set of gamma minus 1. Okay. So that's simple. So if the group gamma has property FW, then you can construct a set of hypersurfaces which is just A up to a finite difference and which is fixed by the group gamma. So that's what you get from property there exists a B. B is just A minus finitely many hypersurfaces plus maybe finitely many other surfaces, hypersurfaces. And this set is invariant. So now what is the variety? Why? You just blow up to get F1 up to FL into the model Y, and then you remove E1 up to EM, basically. Okay, so that's the idea. Okay, so now I want just to use one more minute to, so that's the proof of the theorem A, so it's quite simple. So now I want to use, to explain theorem B. So for theorem B, in fact, we need to rely on works of Danilov and Ghizzatulin. So we apply this strategy for surfaces. And if you use what Danilov and Ghizzatulin did in the early 80s, they studied automorphisms group of affine surfaces. And they look at the compactification of the surface. And they show that if the group of automorphism is very big, then the compactification is by a chain of rational curves, or by a cycle of rational curves. In the first case, they organize good compactifications in such a way that the group acts on a tree. Okay, so the tree the group is acting on is basically compactification of the surface by chain of rational curves, and two compactifications are linked if you can go from one compactification to the other by an elementary transformation. So one example is just the automorphism group of the affine plane, which it is very well known that it acts on a tree. So we use the first statement about groups acting on trees to rule out this case. And the second one is when the group acts I mean, when the group acts by automorphism on the complement of a cycle of rational curves. And then we use a Farley theorem. Okay? So what is the link between compactification by cycle of rational curves and homeomorphisms of the circle acting by locally like PSL2Z? It's the following remark. If you have an affine surface U and an automorphism of this surface such that the compactification of the surface is just a cycle of rational curves, then the indeterminacy when you compactify are just the singular points of the compactifications. And locally, the map looks like a monomial transformation. A monomial transformation is just a PSL, an element in SL2Z or GL2Z. Okay, so that's the link. Okay, I stop here because it's already...